It's really quite a pleasure to be here, and despite the slight mishap there, I also wanted to congratulate the production team here, who is quite amazing, and among other things, gives new meaning to thinking outside the box. So I want to thank them for that. It's really great. So what I want to do today is tell you just a little bit about the kind of physics that's going on today. I'm a theoretical particle physicist and also thinking about cosmology. I think about what happens at the smallest distance scales and the largest distance scales. So I thought what I would do in this brief talk is give you a little bit of the ideas that I talk about in this book, Knocking on Heaven's Door, about how scale helps us organize our thinking about the universe and ties together some of the ideas that we've been hearing. So the one thing I want us all to keep in mind is that we've heard a lot about technology, we've heard a lot about stars and planets in this session, we've heard about things that we can really visualize. The kind of things that I work on and my colleagues work on are hidden. They're things that only get revealed through very advanced technology. We don't see them with the naked eye. And even as basic as what you learned about the atom. You learned about atoms, when people first thought about atoms thousands of years ago, they thought about them as indivisible, unchanging objects. And the beauty of physics is that we were able to explore inside that and find out what atoms truly are. The fundamental building blocks of nature around us are not fundamental. That is to say, they can be divided. And they can be divided into a nucleus, that small point in the center, with electrons around them. And the history of physics in the 20th century was repeating that, getting to smaller scales. And so inside the nucleus, physicists discovered there were objects called quarks. And today, as I'm going to be talking about, we're going to be exploring even smaller scales to try to find out what ties together the mysteries about these fundamental objects that we know about today. So I'm going to start with a kind of funny picture that seems to have nothing to do with this talk, which is obviously of Paris. Somebody sent me this photograph for reasons that will become clear in a minute. And in it you see, of course, the Eiffel Tower. You see a kiosk with a poster on it. And what I want you to think about is that the fact that you see the picture like that is very much determined by the scale of the photograph, by the picture that was taken, by the resolution with which we looked at something. That is to say, if you looked in finer detail, if you were up close, or you had something that allowed you to see much more detailed structure, technology, you would see the magnificent iron gridwork that underlies it. And of course, if you were up in an airplane far away, you wouldn't see the Eiffel Tower is there at all. So basically, as we explore the universe, it's a very exciting time right now. We're exploring the universe at smaller scales and larger scales. And I do theory that can tie together these very different scales of what's going on and try to figure out what are the underlying ideas that tie them together. But we have to keep in mind that much of what we're exploring is invisible to the naked eye. Even though we don't see it in our daily lives, it's there. And even though our intuition isn't built around it, those physical laws are real. And the reason I really showed you that photograph was because there was something else that was hidden, not just the iron gridwork of the Eiffel Tower, but if you blew up that picture enough, you would see that actually the poster that was there had my name on it, which was why someone sent it to me, and that's because we wrote a little opera about physics that premiered at the Pompidou Center. But let me just take you on a very brief tour of the universe just to give you an idea of the range of what we're considering. And then afterwards, I'll focus on one of the most major discoveries that's happened in the time that I can remember and will lead us forward today. So that was not supposed to happen. So large scales. So we can think about the scale of the universe. And when I say the scale of the universe, I'm talking about the scale of the visible universe. The visible scale of the visible universe has a finite size. The reason for that is the universe has existed a finite amount of time, and the speed of light is finite, and that's the fastest anything can go as far as we know. which means that even if anything existed beyond this scale of 10 to the 27 meters, we wouldn't see it. We would have no way of observing it. We can think about it with theory, we can think about ideas, but we can't observe it. And because I'm short of time, I'm not going to run through all the scales, but I'll just point out that 10 to the 27th is 27 factors of 10 bigger than the size of the human being that's at the bottom there. The other thing I want you to think about is the fact that the same laws of physics apply over this enormous range of scales. Our theory of gravity, our theory of electromagnetism. It's magnificent, and it works over this entire range. Why do we explore small scales? Well, one thing is to find out what's there, but the other reason is because in some sense we discover new laws of physics. We discover new underlying ingredients and new forces or laws that tie them together. Even new ways of thinking about physics altogether. And this plot has more on it than I can go through in the short time I have. But what I should try to point out at the top is that even in understanding ourselves, you would think maybe it's the easiest thing for us to understand. After all, we're right here, we can study it. But without developing technological tools, even the understanding of our own bodies we didn't understand. Until we cut to open human beings, we didn't understand how blood flowed or the role of the heart. Until we had microscopes, we didn't know about red blood cells. Until we had X-rays, we didn't know about the helical structure of DNA. So even in understanding how we work, we need to develop this technology. And to get to the scales that we're currently exploring in physics, we need even bigger, even more magnificent, even more advanced technology to get to these very tiny scales. And when we get to these scales, new things get revealed, new laws of physics, new ways of thinking about physics. Nothing could be more dramatic than the change in the way we think about things when we get to atomic scales, the scale of the atom. When we get to the scale of the atom, we need quantum mechanics, which is a whole different way of thinking about physics than classical physics. Classical physics is still correct for most of what we do because you need advanced technology to get to the point where the effects of quantum mechanics appear. But when you have quantum mechanics, you have a whole new way of thinking about things. Today, we're at an even smaller length scale that's being studied through experiments happening at what's called the Large Hadron Collider. Hadron is a name that's being used for proton. It's a large proton collider. What that picture is supposed to show is that you have this giant tunnel, 27 kilometers in circumference, underground, about 100 meters underground. At that collider, protons get accelerated to enormously high energies, and then they're diverted so that they collide. They collide in regions where experiments are built around them. So what happens is through E equals mc squared, we can have protons turn into energy, mass turns into energy, and that energy can then be used to create new particles that can tell us what's happening at distances 10 to the minus 19th meters. That is to say, 19 orders of magnitude smaller than the scales with which we're familiar. I'll tell you in a moment why we think that's a really interesting scale to study, but I want to tell you just a little bit more about the magnificent machine and experiments that are running today. So that is the Large Hadron Collider. That's the tunnel. That gives you the location, which I failed to say. It's near Geneva. It's near the French-Swiss border. And what you see on that are not only this giant ring, the location of the ring, you see it's in a magnificent location near mountains and a lake, but you also see locations where these experiments are built. So I'm now going to show you some quick videos to give you a sense of what actually happens there. Because what happens there seems so removed. It's discovering things at this scale of 10 to the minus 19th meters, but it's this giant, enormous technology that allows us to do it. So what happens is, this doesn't work. Okay. Can we run the video, please? If we can't run the video, can we skip it and go on? Because, okay, well, I will pretend there's a video there. So, while they figure it out. What happens is protons are injected into a bunch of rings, then they go around this ring. And I encourage you to go visit the Large Hadron Collider if you can. It's this giant tunnel. You can actually walk through the tunnel right where the protons get accelerated when it's not running, which will happen next year, where they shut it down. for upgrades to higher energy. Those protons go around, they collide, and then giant experiments are built there. Those experiments measure anything they can about the properties of the particles that come out. They measure charge, they measure energy and momentum. Okay, physics, what are we going to learn there? Why are we doing that? We're going to learn tremendous things about the fundamental nature of matter. We're going to learn, and we already have learned something about this, how elementary particles acquire their masses. This might sound really strange. You think of mass as a property that particles should just have. It's one of the things that define them. It turns out if particles had masses from the get-go, the theories would be nonsensical. You would make nonsensical predictions, like probabilities of interactions greater than 1. It turns out you actually need a mechanism, an underlying mechanism to explain these masses. And that mechanism has now appeared in the news, and it's called the Higgs mechanism. It's named after the physicist Peter Higgs, although other physicists have worked on it clearly. And the sign that this is right is a particle called the Higgs boson, which I'll tell you a little bit more about. It's something that you might have heard called, which Andres kept asking me to talk about, the God particle. We physicists don't call it that. We call it the Higgs boson, and I'll tell you about that. That's one of the things we are definitely learning about because the particle has been discovered. It was a tremendously exciting discovery. And right now we're going on to hopefully learn other things that the Large Hadron Collider was designed to tell us. It not only will tell us how particles acquire their masses through the Higgs mechanism, we're hoping it will also tell us what explains the weakness of gravity, or turning it around, why particle masses are what they are. Why are they so light? We would have expected them to be much heavier. Why are these particles so light? An equivalent formulation is, why is gravity so weak? And one of the reasons that's such a tremendous question is in answering that, we have the hope to learn fundamental things about the nature of space and time. Because answering this question turns out to be not very simple. It turns out to answer this question, it almost definitely will reveal some big ideas, which could be something like an extension of the symmetry of space and time, the symmetry that tells you physics looks the same in any direction. No matter which direction I point my experiment, I'll get the same laws of physics. That's the symmetry of rotation. That symmetry gets extended into the quantum regime in something called supersymmetry. It could be something else that I've worked on, which is an extension of space itself into an unseen dimension, beyond the 3 dimensions that we're familiar with, left, right, forward, backward, up, down. There could be an unseen dimension of space, and the strength of gravity can effectively vary across that dimension, which would be an exciting possibility. Again, something that the Large Hadron Collider could tell us about. And finally, something that we anticipate we might learn about is the nature of dark matter. The matter that we know exists because of its gravitational effects. We've seen the gravitational effects in the universe. That's okay, we'll skip the video, it's okay. Oh, I guess we will do the video. Sorry, okay, let me just finish the statement about dark matter. We'll go back to the video. Okay, which I didn't make, someone on the Atlas experiment made. I just want to make that clear. But we could also learn about dark matter, the matter that exists. It doesn't interact with light, but we know is out there in the universe. Surprisingly, there's about the same amount of it. There's about 6 times the energy of dark matter as in ordinary matter. So many people often ask me, do we really know dark matter exists? Isn't that strange? But I actually think it's more strange that we should be as significant a fraction of matter as we are. I mean, in principle, we could have been a small part of the universe, and even smaller. There could have been 1,000,000 times more dark matter. Yet the amount of dark matter is comparable to what we have. So I guess the video is ready. So I'm going to go back and show you just the video of what protons look like. So we're just going to take the path of the protons around the ring in the tunnel. And like I said, you can really visit this tunnel, see these tubes, which contain these 15-meter-long magnets that keep the protons going around. They collide together in this collision region. And when they collide, they turn into other forms of matter. We hope it's matter we haven't seen yet. And one of the great challenges these experiments have is to distinguish what's standard model, what we know about, from what's non-standard model. What this second video is showing you is that there are many different layers of this experiment. And as these particles go through, everything that comes out is measured, and you reconstruct, you figure out from this enormous mass of data, you have to go back and figure out what was there. In this particular example that the video was made about, it's a particle called the Z boson. It communicates a force called the weak nuclear force, the same way a photon communicates the force of electromagnetism. You don't see that Z boson directly, it decays into other particles. And you find out about the Z boson by reconstructing what was there. And that's what we hope is going to happen with some of these new particles. It's what happened with the Higgs boson, which I have a couple of slides about, and what we hope it will happen for particles that tell us about supersymmetry or extra dimensions or something we haven't even thought about. So this is just a plot that shows you nothing, except that that's the Higgs boson. That is the Higgs boson. The Higgs boson turned into other particles, went out through that detector, and that's what was measured. And by looking at its strange properties, we try to find out about these other things. So I'm just going to conclude by saying that the Higgs boson is not the final word. Right now, they are studying its properties in detail, in part to tell us, where do we go from here? How do we learn about some of these other things that underlie what we see? The LHC is not, Large Hadron Collider LHC is not designed to just look for the Higgs. We want to know what else is present. This is a scale telling us about the matter of our universe, and maybe even space and time that underlies it. So we've come a long way, but we have a lot to learn. So I'll just close with one slide that was actually from the Pompidou Center performance of our opera, where they're trying to discover what's going on, one through exploring the extra dimension, one by looking at the experiments, by seeing what's here. And we hope that in the future, we too will be able to explore further and learn more about what's in our universe. Thank you.